Hi, I'm Ms. Boom. Let's evaluate limits. Example 1. Let's find the limit of 2 of x as x approaches 5. We're going to use a substitution. We can just plug in wherever we see x as 5, and then we can find out that the limit of 2 of x as x approaches 5 is just 10. Sometimes that works, but sometimes we get something like this. The limit of x squared minus 9 over x minus 3 for x approaches 3. Now we can see a problem here because as x is 3, 3 minus 3 is 0, the denominator is 0, so that wouldn't work. So what do we do when we see something like this? So instead of substituting straight away, we're going to factorize. So let's factorize this. So x squared minus 9 becomes x minus 3 and x plus 3. So now we can cancel the x minus 3 and we're left with the limit of x plus 3 as x approaches 3. So we can do this by substituting the x equals 3 into there, and now we have 6. Notice the working out and be very careful with this. See, as soon as I substitute x is 5, I remove the word limit x is 5 because we're evaluating already. Whereas over here, because I'm factorizing the function and I haven't worked out the limit, I still have the word limit in my working out until I sub it in. So in this line, I've subbed it in. So the next line doesn't have the word limit. What are the two things we're going to do today? Substitution and factorizing. So for this graph, we can see that it looks like that. X doesn't exist at 3 because it will explode or it'll make a hole. And therefore, the limit is 6 for that graph as the left side and the right side is approaching the same value. Example 3. The limit of x squared plus 2 as x approaches 2. This one we can just sub it in because there's no denominator that's going to be 0. So we sub it in and we remove the word limit. So we have 4 plus 2, which is 6. Example 4. You try this one. This time we're going to put in negative 2 because it says x is approaching negative 2. We sub it in and we obtain 12 plus 4 plus 3, which is 19. If a function f of x is continuous, where x is a, then the limit of a is just whatever the value is. So for this graph, we had no hole at the value. So there wasn't a hole at 2, there was no hole at negative 2. When I say hole, means there's no that little circle, white circle thing. So these two graphs were both continuous at that point. So that graph was continuous at 2, that graph was continuous at negative 2. So the line continued. Then the limit is simply worked out by plugging the number in. That's what it's saying here. The limit of the function as x approaches the number, so negative 2 for example, then it's just the function at negative 2. So the limit of f of x as x approaches a is just the function at a. Example 5. Pause the video and give it a go yourself and unpause to check your answers. And when you check your answers, make sure that you've written the word limit in the correct lines. So here we factorize because we can see that as t approaches negative 1, that the denominator becomes minus 1 plus 1 is 0, so it won't work. So we have to eliminate that denominator by factorizing and cancelling out any common factors. Now we're left with, notice that I still write the word limit there because I haven't evaluated it. So we're left with the limit of t approaching negative 1 for t plus 1 this time. And we can substitute that, it won't explode. So now that we're substituting, we're getting rid of the word limit. So we've plugged it in. So put negative 1 where t is, and we're left with 0. That is a value. So the graph approaches, as t approaches negative 1, the limit is 0. If a function f of x is continuous, then the limit approaches the substitution. But if it's not continuous, then you have to factorize first. Example 6, give this one a go yourself and pause the video and then unpause to check your answers. So here it says sketch the graph. When you're sketching, make sure that your graph matches mine in the sense that it has a black dot for the parabola part because there's an equal sign there, but there is a white or empty circle for the linear part of the graph because there's no equal sign there. So it's asking for the limit from the left as we approach 2 and the limit from the right as we approach 2. So from the left, or when x is less than 2, we're looking at that and we can see x less than 2 is this equation there. So we substitute the 2 for that equation. So when we plug it in, we get 2 squared, and that is 4. So remember, the negative sign on top there just means we are using the equation that's approaching 2 from the left side. Now 2 from the right side, so over 2 would be that line there. So looking for the limit for x is approaching to 2 for x minus 1. So sub it in. Notice that I don't put the limit when I sub it in. We get 1. And we can see it from the graph. From the left side, it's approaching 4 as x approaches 2. And from the right side, as x approaches 2, the y value is approaching 1. So does the limit of x approaches 2 exist? Well, 4 is not equal to 1, so the left limit and the right limit don't match up, so the limit of the function at x equals 2 does not exist. Just to clarify, we're looking for the limit at 2. If we had looked for the limit, say, at 0, we can see the left and the right exist, and we could prove that by showing the working out, and we can say that the limit does exist at 0. But for the limit at x equals 2, you can see it doesn't exist at all. Example 7. Find the limit of x squared minus x over x minus 1 for x approaching 1, and then sketch the graph setting the values of x for which it is discontinuous. We can clearly see that when x is 1, this is going to not work out because the denominator is 0. So we have to first factorize. So factorize, cancel out the common factors, and we can now work out the limit of x approaches 1 for just x, which is 1. So the limit of this is equal to 1. So let's sketch that. So the limit of x approaches 1 for the function is 1, even though we can see that from the denominator, there's a hole there, the value doesn't exist. And so the function is continuous for all values except for when x equals to 1. Now the algebra limits looks like a bit confusing, but it's just saying that if you had the sum of two limits, then you can separate them, work them individually and add them together. If you had a multiple of two limits, so the limit of k times a function, then you can take the limit of the function and multiply by k later on. Same thing with the multiple, the limit of this function times that function, then you can separate them, work out the limit of the individual ones, then multiply it, and you guessed it, for the question, it's the same pattern. If it's a limit of something divided by something, you can find the limit of them individually and then divide after, as long as the bottom thing doesn't give you a 0, of course. Example 8, the limit of this monster. So what we have described just now is that we are able to find the limit of the top and the bottom and then simplify to find the total limit. We can see that we can factorize this. X squared minus 25 is x plus 5, x minus 5. And x squared minus 3x minus 10 is x minus 5, x plus 2. Double check, minus 5 times 2 is minus 10. Minus 5 plus 2 is minus 3. And we have to factorize because we can see that as x approaches 5, 5 minus 5 is 0, the denominator becomes 0. But as we factorize, we can also see we can cancel this common factor, so we can evaluate that limit. So as x approaches 5, we don't have a problem with x plus 5 or x plus 2. We can evaluate by subbing the top and subbing the bottom separately, and now we have 10 over 7. So you can see that when we have a quotient or we have something divided by something, then we can still factorize and evaluate the limit for the top and the bottom, and then put them together. Okay, thank you for watching, and give it a go again if you need to practice to see if you get the same answers. And I'll see you next time. Bye.